Welcome to our ninth lecture. Today we will continue the topic of last lecture and then to discuss how to work with a trained SOM and then how to render your model. And with this diagram, we would like to remind you that currently we are at this stage. So we are basically at the kind of end of our experiments. And then so the first question following with the last lecture is, what is the trained SOM good for? So because in the last lecture we introduced what self-organizing map is, how it works, and how we are going to train it. And then we implemented with code in Mathematica, and also we introduced the code how to train your own SOM use on top of the tweets you crawled. And then, so today we are going to look at how, what can we do with this trained SOM. And so before we go into tweets, I would like still working with some dummy data set. So for example, imagine that we train a SOM with some apples, as I showed before, that you can describe apples with size, colors, whatever. And then, so imagine we have a SOM of apples, then basically each cell of the SOM can be visualized by some apples. And then as we can expect it that these cells are similar between their neighbors, and then they make a kind of smooth changing patterns. So for example, in this case, in this diagram showing here, that I have a red apple on the top left corner and then a green apple at the bottom right corner. And then somewhere in between, there's an orange or yellow apple. And then, so the first thing we can do with SOM is actually clustering. So because imagine that we have a huge data set, and then we know that there are some items that kind of similar to each other within this data set. But then because it's too large, we are not able to figure it out by ourselves manually. Therefore, what SOM did is, the first thing what SOM can do is to sort them out, to do this kind of clustering task. So for example, on the left, if you have a bigger SOM, then each cell contains like a more specific type of items. For example, maybe all the red apples are on the top left corner. And then on the right, so imagine if we have a super small SOM, and then something that are not very similar on the left side will become quite similar on the right side. And then therefore they will fall into the same cell. So they become the same cluster. So basically, by playing with the size of the SOM allows you to cluster your original data into different number of clusters. And then of course, this size we determined it by ourselves, and then we kind of choose how large the SOM is fits our question. And then this thing is especially helpful, is extremely helpful, especially when we have a very huge data set. And then by doing clustering, we can quickly, let's say, have an overview of what is going on in our data set and which part of the SOM correspond to which type of the data, and then what do they mean, what's their interpretation for us. And then this is the thing we can do. So the first thing SOM can do for us is clustering. And the second, what SOM can do is to make predictions. So as we introduced last lecture, that what SOM did is to kind of a projection from the feature space that we make for our feature vector to the two-dimensional space, which is showing here on the grid. But also what we, and then we also introduced the concept of best matching unit. But then there's a trick that we can do, is that when we are calculating our best matching unit, we don't use all the dimensions of the feature vectors, but instead we use some of them. So for example, here, imagine that we have 4-dimension vector to describe our apples. For example, color, size, weight, and sweetness. And imagine then then we can make a setup saying, can we predict sweetness by knowing the first three variables? And in this case, we are looking at best matching unit using only the first three dimensions. And then, then for example, I have an yellow apple here, and then I only have the first three values of these feature vectors. I feed these first three values to the sum, and then use the exact same algorithm method to calculate the Euclidean distance of these three values to all the cells, and then find the cells that has the minimum distance. So for example, that maybe in this case, I find the cell that contains this orange apple. And then in this case, the sum will, not the sum, but us, we will kind of assume that if the first few dimensions, they are similar, then we assume that the last dimension, they will be similar in this, and then we will use the last dimension of this best matching unit as our prediction for the sweetness of the input, which is the yellow apple. So this trick allows us to, for example, if our feature vector is kind of combining different, let's say, information, for example, for the tweets, maybe we combine both vectors by the image and then the vector by the text. We put them together, and then it is possible that we can only ask for the BMU using the imagery part, and then we use the text part as our prediction. So that, for example, we can say, okay, what is the is the description of this given picture will be positive or negative, something like this. So this will be the second thing that SOM can do, which is make predictions. And then also on top of the third thing that the SOM can do is, on top of the clusters, we can actually creating our own labels or personal labels. We can give meanings to each SOM cells. So because what SOM has present us is a flattened, let's say, grid or map that contains different objects. But basically, because each cell are quite similar to its neighbors, actually, it's not very, let's say, explicit that where will be the boundary between a group of similar cells and the other groups of similar cells. And then therefore, this makes it possible for us to kind of add another layer of meaning on top of it. For example, we can say, and then the best thing of this is that these meanings can be personal. It doesn't have to be something objective. So for example, we can say that, okay, I like the taste of this part of apples if I've been eaten different kind of apples. And then I can say, okay, this part of apple is too sweet, it tastes like sugar, not like fruits anymore, or it's too sour that I don't like them. Or there's another type of there's another group of apples that I simply likes how they looks, something like this, that we can actually give different meanings for the labels, and then later we can project these meanings back to our original data item, so that we can know that what is going on in our data. And then in this case, it will be called a reverse data visualization. I will call it reverse data visualization. So we know that the SOM can be used to visualize our data. If we have a huge amount of data, we can visualize them using this grid. And then if we already give some meanings to the SOM cells, then we can, let's say, visualize this kind of meaning, for example, using different colors, back to our original data. So for example, if the apple data are collected with geo coordinates, then we know, okay, these apples are planted in this area, that apples are planted on that area. And then based on our own taste, own personal label, we can visualize these areas, we can color these areas based on our personal taste. Then, for example, we can have a map of Apple producers that that shows our preferences on top of these Apple producers, for example. And then basically, there are also many other different uses of song, but then they will all be staying with the concept of best matching units and then the clustering, these two. So because with best matching unit, it's actually it tells us many informations already. So because you know that what are the other similar objects within the given data set to your to the one that you use to fit the sum, and also you know that how many other similar cells are similar to the original cell, and so on and so on. And also, if I have, for example, data from two origins, two original sources, I can project them to the same sum and to see what are the distributions of best matching units regarding these two different data sets, and then we can somehow get an idea if they are similar or not. So, for example, if the location of all best matching units, if we sum them up and then show it like a grayscale map, if their locations, if where are highlighted are more or less in the same area, then we can say, okay, these two are quite similar to each other, and otherwise we can say they are not. So many let's say applications that we can do with self-organizing maps. And then, so the first part is a kind of in theory that what the SOM allow us to do, and then the second part will be a short demonstration how we will use it to on top of our trained SOMs using tweets. And then in this case, I was showing you a SOM, I think. Yeah, I was showing you a SOM trained with these data. You can, if you are interested, you can play with it. It will be the second link of the mathematical file. And then, yeah, so you see these are the file I have, and then basically they are all collected in this format near geo coordinates within a certain radius and then a date. So this will be the how this cell or how this SOM looks like. It's 20 by 20 SOM, and then contain all the tweets that have been shown you. And then, as I said, we can highlight those best matching units of data collected from different locations. So, for example, I've collected tweets from all the Swiss cities, for example, and then I can and then I can group my data based on where they've been collected. For example, some are come from Ruhr, some are come from Zurich, and then the first step is I use all of these data to train a bigger SOM that represents all the things happened in Switzerland. And then after that, I choose these two small groups and then ask for the best matching unit of all the elements of these two small groups. And then I will show these best matching units as a grayscale map, or or the brightness of each cell showing here kind of reflect how often this cell becomes a best matching unit that belongs to this group. So for example, then in this case, if I do this, then you see that in Ruhr, there are more best matching unit cells lies on the left side, which are the landscape, water, and also trains. And there are few in the center is buildings and people, and then very few on the bottom and on the right. But the data from Zurich is kind of opposite. So you see less landscapes and then more in compared, more people, and also more, for example, this case, lecture halls, and then meetings, and then also I think this one slides. So you see that immediately with the SOM, we know that something is different between these two groups. That if we do this. And also, for example, we can group our data not based on locations, but based on, let's say, time. For example, on the left, it shows all the best matching units of the tweets, all tweets collected between, posted between 2015 to 2017. And then on the right will be the same thing, but for the tweets from 2017 to 2019. And then you see that well, in general, their distribution kind of quite similar. They both have people, they both have landscape, but then still you see some difference because, for example, on the right side, there's more landscapes and then also more text and books on the bottom. And then on the left side, it will be less landscapes and also less, for example, books, but more concentrated on people and then the lectures. And then this, for example, this kind of stuff. So, and also because as we've been talked in the last lecture that actually many items from the same dataset shares the same best matching unit, and then therefore we can actually ask for what is happening within each SOM cell. So, and then in this case, we can actually select one cell and to see what are those elements that that choose this cell as its best matching unit. And then we can make further renderings for that, or train a deeper SOM or a sub-SOM on top of this, all these elements within these cells. And then of course, we can explore not just one cells, but many cells. And then in this case, we get a feeling on what is going on inside. So then imagine that the first step for us may be, okay, we have a rendering of this SOM, and then we have a quick look what's going on. And then for example, in this case, I see this here surrounded up here, all the cells are kind of showing peoples, and then I'm very interested in peoples. Therefore, I kind of select this cell and to see what's going on here, for example. And so basically, there are still many other things that we can do. So, but basically, with the slides, I think these are the most typical cases, and then we kind of post them here. And then later we will explain more examples for you using the code directly. And then, yeah, I think for my side, the slides will be here. That's it. And so, Carla, shall we explain the task as well, or I should?
No, I think you should continue with the code, and the task goes at the end.
Okay, okay, and I continue. Good. So, yeah, so following with a very quick slides, I will introduce you today's code, not this one, this one. And before we start, please go to our Chairs website to download today's code, because the code we are looking at, it has a small update from the last time. So here, working with SOM, we kind of add few things, new things. So please have an update. And also, if you already have your own SOM, you can work with your own SOM. If you haven't trained it yet, you can also play with the dummy data we gave you. So today I will show you example using the second dummy data. And yeah, I've kind of already run this cell, which is specifying the working folder, and then import a saved SOM, because this takes some time. So I run it in advance. This takes like 1.5 minutes. I think it's not very good to wait for 1.5 minutes. And then, yeah, you see that here it's actually a bigger SOM compared with last time. I have, I think, 20 by 20 cells, and then it contains, I think, around 30,000 of tweets. But then you see most of them are without images. Therefore, it kind of fall into the bottom left corner. And then So today, instead of visualizing the sums and then save some as cells, I will use this sum as example to kind of explain the third chapter, working with sum. Yeah, but I cannot explain this guy, so I will skip it. And yeah, working with sum. So I have four subsections, four sections overlay to dataset. So in I cannot show this one, but I will quickly explain. So usually, well, usually this is the one that we do. It's a thing that we do quite similar. Oh, this slide is very slow for today. It's a thing that we do quite similar as this slide shows, but instead that this song may be trained only using data, for example, from 2015 to 2017, and then we have a collection of new data, and then we kind of project it on top of the old song to see what's going on. But then because here I don't have another data set to compare, and also this thing can be partially, not completely, can be partially done by the trick showing here, which is first gather two data sets as one huge data set and then train the sum, and then further to plot the BMUs using the original group. So I will not actually showing, but then conceptually, this is the part that you use your own song to kind of give it to the new dataset and to see what is going on. And then I will so kind of start with the second one. So highlight songs by locations or time or keywords. So basically, this is the part that we start to navigate within the song to see what is going on. And then there are three parts: by location, by time, and by keyword. This keyword is the one that you use to crawl the data, not the one that kind of extracted from the text contained by the tweets. Yeah. So by location is a little bit tricky. In order to do so, it's required that your data was collected using geolocation. For example, here, if you go into my dummy dataset, you see that actually all the names of the folders are kind of near some symbols, and then there's a coordinates. For example, 46.81, and then 07.14, and then within certain radius things until. So the requirement for doing it in location is that all the data are collected using a geopoint, which means it has a name that near some location within some radius. So otherwise, Mathematica cannot tell where is the original location of this song, and then therefore it's of this data, and then therefore it's kind of tricky to do it. And then so the first thing we are going to do is to actually find all the locations within this song. So what we are doing here is we do kind of reverse interpretation that to convert the geo coordinates back to the name of the cities. So yeah, so with this function, I kind of parse the geo coordinates back to the name of the city using OpenStreetMap. So OpenStreetMap has API that you can feed the coordinates in, and then it will tells you the name and also boundary and other information of the location. And then here, these are the cities I've been collected from my dataset. And then the second step is I will copy paste. So remember, this is kind of important that I need to copy paste the name of the city from the locations here. So for example, I need this one to represent Zurich, and then copy paste it to here. It looks kind of different though. To copy paste to here. Come on. Yeah. Yeah. And then it should tell me exactly the same coordinates, which means the name is okay. And then I can say highlight song by geo coordinates. The input will be our song, and then the city coordinates, which will be this one. And then using image method will be image. And then of course the method you can change to keywords or to the closest image or to the number of elements within each cells. So hopefully it will be fast. It's a little bit slow. Yeah, because this SOM actually contains more data than the previous dummy data set. And also Mathematica has been very slow on loading images for some versions. Yeah, okay, great. Yeah, so these will be the result of highlighting our SOM using data collected from this city, which is Zurich. And then actually you can see that here the number of name is actually equals to, if you only look at the first parameter, which is the coordinates, it's actually equals to how many coordinates I have here. And then I can do another test, which is, let's try this one. Copy it here, and then it gives me another coordinates, so I can confirm that this is correct. And then I will copy this line again so that we can see the differences of the two results. And then again, I will run this cell, run this line. Yes. Ooh, it's quite different. So I will try to make it smaller, maybe. Not sure if it's possible. Doesn't change. Yeah, and also this guy, make it smaller so that they fit into the same. Okay, I'll just copy, paste, copy, paste. I kind of copy paste these two outputs and then put them into the same row, and then you can see what's the difference between these two. So obviously, the result of the second try gives us more activation on landscapes, mountains, lakes, rather than things happened on the right, which is, yeah, lectures, halls, people, yeah. And then the last step is we can do is to actually render these elements out. And I think combining with the location of the best matching units on the SOM, and then also the rendering here, for us it's already possible to kind of interpret what is going on in this area, in this geo area, and as well as in this area of the SOM. Yeah, so these will be the rendering. And then the good thing of this rendering is that actually oops, come on, yes, actually every image is kind of hyperlinked. Therefore, if you click at this image, it will bring you back to the original tweets. As long as the author didn't delete these tweets, you can still see the original tweets. And then, for example, we can try this one. Yeah, gives me this original image. And then what this rendering means is that this rendering, similar as the SOM, it will also try to plot similar items close to each other. The difference is that this rendering doesn't do kind of clustering, which means it doesn't compress the original data into certain clusters. It will post everything into the same plots. Therefore, I think it's a good way to actually visualize something when you want to use all the things you have rather than just want to use the certain cells, BMUs. But on the other hand, when you try to navigate through it, I think using BMU is a better option because then it gives you a much clearer idea on what is going on rather than to detail the checking one after the other in this plot. But then I think this is a good way of showing data in playing with the visualization in different ways. Yeah. And also for the second, it will be very similar that we can not only showing data by the geo coordinates, but also by time. And similarly, if we want to do it by time, then it requires our data to be collected with the parameters called since some time and then until some time. It doesn't have to be both included, but at least I think we need to include one. And then with and then what we are doing here is actually using the crawling parameters we were using. We kind of regroup our data into certain let's conceptually folders. That kind of we copy paste our original data into different folders that correspond to different time period. And then in the slide, I've shown already that from 2015 to 2017. So here, maybe I can play a little bit. 2016 to the end of the year. And then let's try what is going on. Yeah, okay. So I will make it smaller. So, yeah, so this will be the where the elements are, where the BMUs are for all the elements collected, posted between within the 2016. And then if you check with the result showing in our slides, it's actually quite different from the others, right? Yeah, and again we can visualize all the data in the feature space as we did before. And while waiting, I will quickly explain the third part. So because with my dataset, it's not possible to do the third part. So the third part is to group your data by keyword. This keyword is the one that you are using for crawling data, not the keywords contained in the text of the tweets. So it's a little bit tricky to always remember this difference. And then with these keywords, actually you don't have to input the entire keywords or the complete keywords. You can, yeah, okay, the rendering is out. Yeah, and then you see that here, actually here is on the left side is the landscape, in the middle is the person, and then on the right side is lecture halls. Well, and then on the bottom there are some food. Can I yeah. Okay, so then I will continue with what I've been reaching. Yeah, so this keyword, you don't have to enter the complete keywords so that to get the result. Instead, you can input a part of the keyword so that it gives you not one but some folders. So why will I do that? So I will explain you with the last tweets I've been working with in the last lecture. It will be lecture 8. Here, all tweets. So for example, here these are the dummy data set I've been using in the last lecture. You can see at the folder that actually, for example, this one is called a symbol Beijing, and then until a date. And then this one is just Beijing, and also this one, New York until some dates, New York until some dates. And then this one is just New York. So what I mean here is that it is very possible that when you're looking at some keywords, sometimes you type it with, for example, hashtag, sometimes without, and then conceptually you, for example, if you are looking at several hashtags at the same time, and then I think conceptually you would like to prefer that those with and without hashtags but contain the same text should belongs to the same group. And then in this case, this key allows you to group this text with and without hashtags into one. So unless I type completely here Beijing and then include or not include this hashtag, otherwise, for example, I can only type BEIJ, so that because all Beijing will contains this BEIJ, and then therefore I can use this as the key that to gather all the Beijing parts into one. And then because here for today's lecture, my dummy dataset actually contains no keywords at all, because I kind of collect everything near the certain location. Therefore, there's no keyword, and then therefore this part I cannot show. But then you can expect that the result visually the result will be similar like this, that you have a song, but different places get activated in a different level, and then the idea is that with this activation map, let's call it activation map, then you can actually start to interpret what is going on, especially when these keywords representing some certain actions or certain locations or certain names, then it will be different. It will be interesting to see the difference between the different keywords and then their corresponding contents. Yeah. So the first part will be highlighting the song, and then now I will jump to the second part, select cells on the song. So so as we said that the each song cell actually contains or correspond to many items from the original data set. Therefore, it's always interesting to have a deeper look what is going on within each cell. And then to do that, the first thing is we need to select cells. And then therefore here we provide two methods to do that. One is select center cell and their neighbors. And then the second is kind of interactive cell selection. The first one will be very fast, especially when you want to select many cells. And the second one is kind of really do it manually. If the boundary of the group of cells you are looking at is not regular, then you probably use the second one. And also before I start, so here the first parameter is which cell to select. Actually here is integers. It indicates the position of the cell you are looking at within the song, and then how these cells are numbered is first by row, and then first by column, and then second by row. So which means I'm not sure if you can see my screen. I will use notebook. Which means the number will be 1, 2, 3, and then until, for example, 20, because I have a 20 by 20 song, and then it will be 21, 22, and until 40, and then so on and so on. So this is how the song cells are numbered. And then therefore, say I'm looking at the 22 and the 22nd and the 44th cell with a radius of 2. This radius means I want to look at not only these cells, but also their neighbors. And then I got two graph visualizations. So you see that actually for the first one, the center cell is at the second column, second row, and then because its neighbors that are within the because it's kind of close to the border, therefore not every neighbor, because then the shape of the neighbors, it doesn't look like a circle, but kind of a circle being cut on top and on the right. And then then the second graph shows the cell 44 and its neighbors, and then you can see what they look like. And then The second, this will be the first option to select cells, and the second one is to do it interactively. And then so therefore we have a function called interactive cell selection. You give the sum and then also the image, the method you would like to visualize the sum. And then here it's possible to use none, which means nothing, which means just an not an edge graph will be are presented to you, or you can use images, which means you will have a sum that looks like this one, looks like the one we were doing highlights. And also you can use keywords, which means you will have a sum that it's really similar when you rendering the sum using keywords. It's kind of colored squares with white text within each square. Yeah, for example, this will be the interactive one, and then you can start to select. And then if you click, then the cell gets red, and then you see that on the bottom it says selected cells 69, 70. Yeah, and I can do it again and again and again. If I don't want one cells, and I will just re-click it, and then it will deselect. Yeah, for example, I can select this part and then this part, so I have 8 cells. Yeah. And then again, I can highlight these cells on the sum, but then since we already know where they are, I will skip this part. Yeah, and then the really interesting thing comes with that we can actually look at the objects within the selected cells. Yeah. So for example, I can say I want the first 5 element shows, or I want the first 10 element shows. And then you also read that here there are in total 135 tweets contained in these 8 cells. And then if I deselect 4, and then if after that I run it again, and then you see that there are only 52 left. Yeah. And then they correspond to, looks like these are ads selling different stuffs. Yeah, so I can, for example, I can select some other cells so that we have more data to play with. Now there are 126, and each one you can still click it, and then it will brings you to the original. Yeah, and then with that we can actually doing 2 things. One is, as usual, we render these objects in feature space. I will not further explain this, so I will simply run it. So here you see there are 2 lines, render query elements, and then they are basically the same except the last part, hyperlink to file. So the difference is that the first one will generate a graphics that the hyperlinks brings you to the original tweets, but the second one the hyperlink will brings you to the file on your computer. The good thing for the second one is that if later you want to working with these images, then it will be easier to find these images on your disk directly rather than to download them again, because when crawling the data, you already did that before. But the bad thing of the second one is that once this graphic is generated, please do not move your files to somewhere else. Otherwise, the hyperlink will not work anymore. Yeah. So for example, with this rendering, similarly, I can click on these images and it will bring me back to the original post. You see that actually here there are many trains and railways, and actually this is a stair, but it looks like very similar like a railway. Yeah. And then the second part is that actually we can render the objects by our crawling queries. So it's kind of very similar to project these 4 selected cells back to the folder we've been, or the parameters, the set of parameters we've been using for collecting the cells. Yeah. For example, we can get the original crawling parameters we were using. For example, near this location, within certain radius, things until. We have actually many, and then here I'm showing only up to 5. I can delete this part, then I show everything, right? And then, okay, I will put it back. And then there's an optional process that you can actually process these strings by your rules so that you can merge something into similar groups. Very similar to what we did before, that we highlight songs based on locations or based on time, because then these locations are also, for the same location, it's also a collection of different folders of different time. Therefore, we can do the same things here. For example, if we can say we can parse, I think I should call it a 2 because I changed the definition of the function, and then later I will give you a corrected version of the file. Currently, I just name it 2. Yeah. For example, I can say I can parse, I can group these locations by the parsed names. For example, then I have I can show everything instead of 5. I have, for example, Geneva, Bellinzona, and also Bellinzona again, and then again, because actually these are the names correspond to different folders we have, and then therefore the number of text here actually equals the number of the folders we have in our data set. Yeah, and also again, if we don't want to do it with locations, we can. But then before we can do it by date time, but before that we need to run the first part, the original query again, so that we replace this Q string with its original value. So now it's near, within, things until, right? And then I can say I do it by date time, and then you see that this Q string actually changed to things until, things until, things until. So everything becomes things until, and then this is the trick that you later you can group them together and to look at, for example, only by time. And then, so let's say I will stay with things until, and then I will show the results accordingly, show a kind of the result in the form of histogram. So I will collect all the tweets of my 4 selected cells, 8 cells, 8 selected cells, and then count how many tweets belongs to each category I have. So yeah, you see that here, since 2018 September 1st until 2019 September 1st, there are 47 cells. And also since 2013 September 1st until 2014 September 1st, there are 30 cells, and so on and so on and so on. And there are 30 tweets, so on and so on and so on. And if I change it again, I change it back to the cities. Now Q string becomes to the location, the name of the location rather than the timestamp. I can do it like this, and then I show the histogram again. Then you see how many tweets were collected by different locations. For example, you see the top 3 are from Geneva, from Zurich, and from Basel. So even if that I did exact the same parameters for every other cities, but the amount of tweets I can have from these 3 cities are actually much higher than the other cities. I mean, at least for the selected 8 cells, this is the situation. And then later, we can still render this histogram in the form of renderings. And then here, it's important that we have to copy paste what we were using here into this rendering. For example, what I was using is the date time. Therefore, I will copy date time to here in between selected events and image size. If I didn't do that, then I will have I will show you what happened if I didn't do that. So because I say that the second part is optional, if I simply forget about them and then I run this original query string, and then I run this histogram, and then this is what I will get. So you see that it shows the result of every folder I have, a histogram of every folder I have. So it's near this location, things until, near this location, things until, and then from this is kind of difficult to get what is going on. Therefore, sometimes we need this optional process to do that, right? And then assume that I will stay with date time, and then yeah, I render this, then you have different results. Yeah, and then because I was using date time, therefore I will copy paste date time to here, and then I will have the rendering. And then similarly, that the first and second lines the only difference is where the hyperlink brings you, either to the original post or to the file on your disk. Yeah. You see, actually, it's a kind of histogram that, again, from different, based on different timestamps. The column of this histogram will be exactly the same as the column in this diagram, and then we have 1, 2, 3, 5, 6, 7, 8 columns. Therefore, here we will also have 1, 2, 3, 4, 5, 6, 7, and 8 columns. And then again, if I click, I know who posted and then where it is. Yeah. And then the last thing we can do is that imagine that we use the SOM as a pre-processing step until before our further analysis, we can actually save the extracted object. In this case, all the tweets within these 8 selected cells into a new file that we can use to train another SOM on top. And this file, it will be this structurally, the structure of this file will be exactly the same as the one generated after we do the feature vector calculation. Therefore, the name I suggest that the name we can give to this file can still start with vec, and then with some other names specified by yourself. Therefore, then we don't confuse this file with the files that are saved as that are the SOM, saved SOM. So for example, I can say it's vec selected, and then I simply save it. Yeah, and then it will be in this folder. In here, it's called vec selected, and then you see that actually is much smaller than the one called vec fe, which is all the feature vectors of all the tweets. Here it's just the feature vectors of the selected tweets, and then with this selected tweets you can again train another SOM and then repeat the similar process. You can even save the files for the selected cells of this already being filtered SOM, and then you can do it again and again and again. But then usually I guess do it again will be already enough, because you already kind of narrow down a lot from the original data you have. Yeah, and then the third part will be to query to SOM. This is kind of similar to the prediction part that has been introduced. The only thing is that here actually we don't get a prediction, rather we get a collection of items, because the input items we have, which are the tweets, are not actually let's say labeled. The labeled means that before they've been used to train the SOM, they already have some meaning. For example, some SOMs are posted by I don't know, by people from Europe. Some posts are posted by people from North America, for example. Then if you have been labeled this data, then and these labels are included in our feature vector, then you can use it to make prediction. But then in this case, because in our feature vectors there's no labels contained, therefore the only possible thing we can do is to retrieve similar items and then interpret the result ourselves. I think for now, let's say engineering tasks, I think this is already a lot. So Also, a query allows you to ask for similar objects by either images or by text. It depends on how your feature vectors being calculated. So, for example, in this case, this sum is trained with feature vectors calculated by machine learning algorithms. Therefore, I will use the first step, which is query by image. So, for example, this is the original the query image I would like to use, and then I kind of pre-process it so that it's kind of square, and then with the size of 200 by 200. And then the second step is how which feature vector feature extraction method I was using. So I was using neural network, therefore I used the third one, right? I will run this step and to calculate the feature vector. Yeah, it's done. And if you ask for what is vector Q, you get a list of numbers. And if you ask for its dimensions, it is 2048. Yeah, this is my vector. And then I will go to the second step, which is obtain the query results. And then the first step will be to ask for the best matching unit of this vector on sum. And then I will run this. It tells me the BMU is the cell number 117. And then I can highlight this one. I will highlight this one. Also, I can select the elements belongs to this best matching unit and can kind of show it as a list. A little bit slow because it's a very large sum. Yeah. So this is the cell of 117. And then later, these are the first 5 elements belongs to this cell. You see that they are all people. I can increase it to 10. Yeah. And also we can, it's similar as what we did with selecting cells. We can see not just one, but many, the BMU as well as its neighbors, because usually what BMU because usually what the neighbors contains are quite similar with the BMU. I think here I have a mistake. I think these cells are not correct. Yeah, and then okay, it's correct. It's correct. Okay, good. And then here I can use I can still highlight these sums. Oops. Yeah, okay, something's not right. Cell selection, radius, cell selection, MU. Oops, this has become seriously wrong. Okay, now it's good. Looks like I've made some mistakes in the code. I will clean it and then give you a correct version. Yeah. And then again, we can look at the tweets within all these cells, right? A little bit slow. Yep. These are my selected cells, and then these are the items within. You see that actually they are all people, but then some cells correspond to individual person, but some others are a group of peoples. Right. And last, the third step, we can also still render our query result in the feature space. And then again, similar functions are provided. Either the link will be go back to the original file or to the hyperlink. I think in this case, I will try the original file. Right. Oof. Looks like we have a lot of people here. Otherwise, it will be not so slow. Yeah. Okay. Yeah. And then we'll see if it works. Yeah, sometimes there's an issue that I have to say, that sometimes this link to original file doesn't work because the format of the address. So if I say copy address and paste it here, you see that actually is a kind of hyperlink. And the trick is, the tricky part is these symbols, these percentage symbol and then 22. So we usually, if you copy paste such link in your web browser, it will link you, it will brings you directly to the file. But then the tricky part is here, is that the browser automatically parse this symbol to the quotation mark, and then therefore we don't have a file named this with this quotation mark, and therefore it doesn't work. The solution is to copy paste the link to your file browser and then delete this file comma / and then it will brings you to the original file. Yeah. This is the tricky part that doesn't work on when data is collected based on geolocations. But when for other data that are collected, for example, with keywords or with hashtags, it works fine. And also the same, the link will still work if you say right-click this. Sorry, right-click this output and then say save graphic as. If you save it as PDF, then the link will still work. So say it's test. Come on. Yeah. Computer's being. Yeah. This is the output PDF, and then you see that actually here every image has a hyperlink contained. Yeah. And yeah, so that I think that will be it. That will be from my part.
Yes, and I will suggest we take 5 minutes of break and then we come back at 9:20.
Yeah.
We can have a look at what you have to present in the last lecture. So I think we can continue with the second part. So I would like you to go to the PDF file we have shared with you. I'm going to share my screen now. So if you go to the folder where we have where you have downloaded the code and the lectures of today, go to the PDF that is called Guide Students. So here we have one first page that is explaining you all the files that you have to have in order for the code to work. So I will quickly go through this page, and then you can confirm or check every time you're running your code. So first you have to create your vector file, and there's some. So here you see, I mean, these are the code that you use to create your vectors, and then you use to create your sum. The second one is the folder containing all your crawl tweets. And inside this folder, a quick reminder again, don't change the images location or delete the GeoJSON file for the crawl tweets. So here inside, you will have, as I said, one folder with the images and one GeoJSON with the same name as the folder. The fifth is the file that the file of the vectors that you create with this code. It can have any ending. For example, here is back with feature extraction, and then also back with semantic analysis. It doesn't matter the ending, it just matters that it's called back and the extension is .m. So the sixth is that if you have already trained on sum and you have saved it, then you will have one file that is called sum, and it has the ending of the method you use to encode your data, and it has the extension of .m. And for example, this is what Guo explained you about if you want to overlay a new data on top of your sum, you have to first crawl new data and then create the vectors of this new data. So these 7 files will be the vectors that you have created of your new data that will be overlaid on top of your sum. So here's just like a matrix where you can check if you have all these files in your folder so you can continue with the work. So I'm going to show you now what we expect from you, or what you have to deliver. So first you have to create one title page. Here you will have one project image. You can choose any of the images that you have created through the process, but you have to have one image, the title of your project, and then a short description. This should be 2 paragraphs. Here, you can take the information you have been writing in the Google Docs where you explain the aim of the project, the questions you have, the hypotheses, and what is that you're looking for in with this experiment. So this is the first page. And then here on top, I give you, there are 4 steps. So the first, you should include the sum either on images or on text, or if you want, you can have both, as I have it here, but it's not mandatory. You can have one or the other. Then you can do this manipulation or comparison. So for example, you say, I get my sum and I'm gonna compare it with the new data that I have encoded, and then I'm gonna see in which are the cells that gets highlighted with that. This is one way of comparison. Another way of comparison is what Guo explained you today in the code. So is if you have crawled your database on, let's say, locations, you can overlay the big sum with specific folders containing each city. So this is another way of manipulation. Or also you can do it based on timestamp. Or here is not included the third one, which is based on the keywords that you use to crawl. But as I said, you can choose any of these to be your second step. You don't have to have them all. You just need to have a way of manipulation with your sum. The third step is the selection. So here you have to filter some cells that you found through this manipulation, and then render them in this feature space. So we see the whole spectrum of the images or text that you have selected within this process of creating the sum, then manipulating, and then selecting. And you can do it in many ways. So for example, here is based on years. So let's say I will only focus on the year of 2016 because that's what I want to look at, or I want to focus on one specific location. Or for example, what he showed you at last is add one image which this is not included in the data set, and I want to find where this image will be placed, and then I can open all the elements that are inside that BMU. You can decide however you want to select your cells. You can do it based on one image query. You can do it based on keywords. You can do it based on location. You can do it based on time, or simply you can just navigate through your sum, and then you can just navigate through your sum, and you can actually select some cells that are appealing for you. In this case, for example, I say, yes, I'm going to go through these cells on the top corner because I like to talk about landscapes now. My question was about how Swiss landscapes look like. So this depends on your question. And that's why the first page should be very clear, stating what is that you're looking for in this data. And using these 3 steps, first by creating your sum. So your sum is created, it's organized depending on the vectors you use to create the sum. So this is very important. So you should address that as well. And if you see in each of these pages, I have also write a little bit of what you have to write here. So for example, here is describe why and which particular method you use to encode this data. So here describe why you decide to manipulate the sum in this way. What is that you're finding in this selected group of data. So just one paragraph that is explaining very clearly what is that you're finding, which were your decisions and why. And one last thing that I had added at the end when you have that you went through all this process is that you're going to render your model. And render your model, we also gave you different ways. So for example, you say, I'm going to concentrate, I'm going to give you a silly example just to exemplify what I meant by rendering your model. So this is the last slide, and I say, okay, I want to talk about Swiss landscapes. And I have selected these top corner, left corner cells. And I say, okay, out of all the images that were included in this cell, I have selected the top 10 images I want to work with. So then I say, okay, yes, out of these top 10 images that I found that are very representative, that I would like to work with, I selected one. And I later will show you this code that is overlaying or is adding a selected images on top of all the other images that you have selected. And what you can do with this is that you can create, for example, in this silly question, a fake landscape that is merging one selected images with every other image that you have. This is one way of rendering your model. So it's kind of giving you an atmosphere of what you're looking for, or what you're what you're searching, or what's your question about. Another way of doing it is also you can select all the images that are relevant for you, and then you can add them together. So here you have, I think, 15 images that are talking about Genève. And this is how, if you overlay all of them, will look like. This is one way. Another way is also you can create a collage. This is automatically generated. I will give you the code for this. The only thing that you have to be careful of is to give grades or ratings to your images. So you have to decide which image you would like to prioritize more and which image you would like to give it less value. And by that, you create this collage with ratings of images that you have selected in order to tell a nice story about your project. You can do it with the code, but you can also do it by hand. There is no restriction on this. the only thing that you have to deliver at the end is one image that is actually relevant to the question you're asking. So in this image, you can show a result or a resolved question you have and a short text of conclusion. What is that you found through this pipeline? And what is that you didn't found? Because usually the hypothesis we set at the beginning are at the end they didn't realize. But the interesting thing is that you go through the process and then you see if you made a mistake or not, if you need some, if your assumptions were incorrect or they were correct. So this is something that we really want to read in your text. So the last, you have 4 steps. And on the last, you have to bring an image that is trying to answer the question you have at the beginning, plus a short conclusion, or did you find the answer? Didn't you find the answer? Or what is that you were, that you encountered during this process? So if you have any question regarding this last task, I will just open up now all your mics, and then you can talk with us quickly after I go to the code, and then I show you how to create this last, this 4th step. Okay, I give you 1 minute if you have any questions. Okay. So if you don't have any questions regarding the last, so what you have to deliver for this course, then I will go to the coding part. Share my screen again. So go to where you crawl, and you see here we have 2 folders. And I will explain you these 2 folders when we open the code. So please open the code that is called 09 rendering your model. So here, what you have 2 ways of render the model, and I gave you a short description of how each of these functions are working. So for example, the first one will add a selected image or combine every picture to the selected image. So when you run this function that is called render model 1, you can ask for EMGS, which is show me all the original images, or EMG1 all, to show me all the images overlay on top of a selected one, or image all, these are all the images overlay on top of each other. So one thing to use this code is first, as Gu will show you with the pipeline, at the end of his code, you will be able to navigate or to see all the images you have selected. So when you are in this, let me just quickly. When you are, for example, in this stage, you will be able to select the images you want to work with, and these images, you have to save them in one folder, and this folder should be in the same folder as this code, as I have it here in my folder. So I have my code here, and I have, for example, here one folder that is containing all the selected images I have found through the process we did. So here I have to put the name of the folder where I have pasted all the selected images here. And then I have to select one image that I found that is more representative in this case. And by doing that, I can, for example, here run this line. And then I'm gonna ask, for example, I want to see all the images overlay on top of for example, why I want to see all the images overlay on top of the one that I selected. So I see that there are variations on the one that I have selected. These are not, yeah, I mean, I silly call it like imaginable landscapes, which is this merge of different images. But I can also, as I put you here, I can also copy and say I want to see all the images on top of each other, and this is what I get. So this is one way of doing. And if I want to check all the images that I have worked with, I can copy the first line, and then I see these are all the images that I have on my database. Great. So the rendering number 2, this is the collage that I show you in the presentation. So here is one step. You have to do one step before using the code. And this step is, again, select all your images, put it in one folder in the same place where this code is. But here you have to rate your images. Rate means that you have to give a higher number to an image that you like the most. And you go in scale till, let's say, 1 or 2 to the one you like less, or you can even, this range you can modify, or you can, yeah, you can control it depending on how your rendering is working. So here you say, I have rated this one as on, it has a 20, and I have this one as 15, this one as 19. So here the numbers of the name of the images are representing how much you're liking this image. So again, what you need to do is say, I want my folder that is called Geneva, and I want the background of my collage to be white. So these are the only things you have to define. So here I run this line, and you will see what I get. So I get this collage I showed you. So you can say, I don't want my background to be white. I want it to be black. And you run again the cell, and then your background will be black. And you can choose any color for your collage. Another way is that you can also work with the same rendering I show you here. You can use, so you see I have called the functions render model 2 and render model 1. So just a reminder, if you want to use render model 2, you have to have your pictures rate. Otherwise, it will not work. But I also can work with the render model 1, and I can say, I know my selected folder. So if I say, what is my selected folder? My selected folder is Geneva. So I know my selected folder, and I know the name of my image, my favorite one. My favorite one, as I said, is this one with the higher number. It is number 20. So if I run this line, and if I say, okay, I want to see an overlay of all the images in one. So here's what I get. And I actually can also ask for the other options. So I can say, I want to see all the images overlay on top of my favorite one. Here's what I get. So these are just a few examples of how can you show us your last image that is trying to answer your question, or that is addressing the hypothesis that you have been posed at the beginning of your experiment. As I said, you can do it as you want, but it should be a representative one. You can do, this collage is automatic, but you can do it again manual. If you want to overlay your images as you wish, you can do it as well. But you have to deliver one model, one last image that is representing this personal model that you have created through this process. Okay. So after I told you this today, I think we will not have time for meeting you in the breakout rooms. But I will like, now that we are all here, it will be good if you if you address some questions, if you didn't get, for example, something in the code, or if you have a question regarding the project you have to deliver. Because next lecture, we will not have a lecture as it is, but we will have a workshop. So in the Google Docs, we will set you a time slot where you will have 20 minutes to ask any question or to work with us to shape your project. You will all be in the call. I mean, you can all be part of the call. We will be in these breakout rooms from the beginning, and Guo and I will be joining you in each breakout room depending on the time slot that you have reserved for us. Yes, so tell us, I mean, if you, I'm sure some of you may have questions regarding your project that you want to address today, then maybe just raise your hand and then we create just groups for the ones that have questions today.